Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about causal inference. In particular, we're going to explain why causal inference is a very challenging problem when you just have observational data and you don't have control over your data acquisition. The reason is that there might be confounding factors or confounders that distort the causal relationships that you see in your data. We will also explain how to adjust for these confounders and under what circumstances this adjustment is going to work out. Let's get to it. We're going to use the same example as we used in the previous video on causal inference. It's this observational study where we want to evaluate whether a new drug is effective or not. We define a random variable t, which indicates whether each patient was treated or not. T equals 1 indicates that they received the drug. T equals 0 indicates that they did not. We have this other random variable y, which indicates whether the patient recovered from the disease or they did not. Recovery is y equals 1, non-recovery is y equals 0. We observe the following data. The probability that the patients recovered given that they did not receive treatment was 0.38. The probability that the patients recovered given that they did receive treatment is 0.68. So should we conclude that the drug is indeed effective? Well, not so fast. First, we have to ask ourselves what these probabilities actually mean, these conditional probabilities. What these probabilities do mean is that indeed 68% of the treated patients recovered and 38% of the untreated patients recovered. That is completely true. But that doesn't establish a causal effect. To establish a causal effect, we would have to determine that if we had treated the patients that we didn't treat, then 68% of them would have recovered. And this is not implied by these conditional probabilities. These conditional probabilities do not imply that if we had given the drug to these untreated patients, 68% of them would have recovered. The reason why this is not implied is that there might be a systematic difference between the untreated and treated patients. In order to capture this notion of what would have happened if we had given the drug to the patients that we did not give the drugs to, we define the potential outcomes, which are random variables that capture the following. The first potential outcome captures what would happen if we did not give the drug to anyone. The probability that it equals 1 would be the fraction of patients that would recover if we didn't give the drug to absolutely anyone in our population. Similarly, the second potential outcome with a subscript 1 indicates what would have happened if we had treated all of the population. The probability that this potential outcome is equal to 1 is the fraction of people that would recover if we had given the drug to everyone. What we actually observe depends on the treatment. When the treatment is 0, then we observe the potential outcome associated to no treatment for that patient. When the treatment is 1, we observe the potential outcome associated to treatment for that patient. What we really want to determine is how the probability that each potential outcome equals 1 compare. Because again, here what we're comparing is the fraction of people that recover when we treat nobody and the fraction of people that recover if we treat everyone. And this is exactly what we want to know, right? What difference would the drug make on the whole population? The problem is that we don't observe this because we cannot take the whole population and give them the drug and also not give them the drug. That's just impossible. Instead, we have to work with this data that we have. In the data, when we don't apply the treatment, then the observed outcome corresponds to the potential outcome associated to no treatment, but we don't see the other potential outcome for that particular person, the potential outcome associated to them receiving the drug because they didn't receive the drug. Similarly, when they do receive the drug, the observed outcome corresponds to the potential outcome associated to receiving treatment, but we do not see the potential outcome associated to not receiving treatment because that person received the treatment. Okay, we call this unobserved outcomes counterfactual because they're counter to reality. We did give the treatment to this person, and we're asking ourselves what would have happened if we had not given the treatment. Let's go back to our example. In our example, it just so happens that there's this important factor that determines the efficacy of the drug, which is the patient age. Half of the people are young, half of the people are old in our data set. So this random variable A, if we look at its PMF, it takes two possible values with probability 1/2. Now, for young patients, it turns out that the drug is useless, but these are very healthy patients that recover at a high rate anyways. So the conditional probability of not recovering, this is recovering, right? Because the potential outcome would be equal to 1. Of recovering if we don't give the treatment and the person is young is equal to 0.8. So 80% of the young people, if we don't give anyone the treatment, would recover. However, if we give all of them the treatment, then also 80% of them would recover. So in this case, there's no causal effect among young people. The drug is completely useless. Among old patients, it's a different story. The drug is actually quite effective. So if we didn't treat any of the old patients, that's what the potential outcome indicates, conditioned on age equal to old, then 20% of them would recover. But if we treated all of them, that's what the potential outcome associated to treatment means, conditioned on old, then 40% of them would recover. So this is actually a pretty big difference. It just so happens that old patients are less likely to be treated because this is a new drug and they're not very trustful of new medicines or something like that. And or maybe they go less to the doctor, who knows. The point is that in this fictitious example, for the young people, 70% of them receive treatment and only 30% of the old people receive treatment. Okay, so there's a systematic difference between how these two subpopulations are receiving the treatment. So now what we really want to do is we want to estimate the efficacy of the drug over the whole population. This is what we really want to estimate from our data. What is that efficacy equal to? We've seen that it depends on age. So we're going to apply the law of total probability and then the chain rule to express this in terms of the probability that the patient is either old or young times the probability that they would recover in the absence of treatment if they were old or if they were young. And these are the potential outcomes. So this would be if we did not treat anyone in the population. Those numbers, as we saw, is 0.5 because half of the patients are old, half of the patients are young, times 80% because that's the rate of recovery for young people, and then 20% because that's the rate of recovery for old people. So overall, the true rate of recovery when we don't treat anyone in the population would be 0.5. We do the same thing for the potential outcome associated to treatment. We do exactly the same thing. We condition on age. And what we see is that the only difference is that the old people do better if we treat all of them. Okay, 40% of them recover. And because of that, the rate of recovery when we treat all of the population is 0.6. So there's a 10% difference. There is a causal effect here. Okay, I mean, I'm no doctor, but 10% seems pretty good for me. Pretty good to me. I don't know what I'm saying. Okay, so now this is what we want. Okay, we would be very happy if we could find this out from our data because this would give us a very accurate picture of the efficacy of the drug. But now what we see is our data. So we have to see how Y behaves because Y is what we actually end up seeing. So we're going to make the assumption that the potential outcomes and T are conditionally independent given A. What does this mean? The first time you hear this, you might be, oh, this is a little bit weird because how would the outcomes and the treatment not be dependent? You have to remember that these are the potential outcomes that don't depend on the treatment. So this is what happens if you don't treat anyone, no matter what happens with the treatment. So basically this is saying that conditionally given age, if you just look, for example, at the young people, there's not a systematic difference between the young people that are treated. Okay, this is why the independence is with the treatment, and the young people that are treated. Okay, there's no systematic difference. Same with the old people. If you take the old people that are treated and the old people that are not treated, then there's no other factors that make them systematically different. So that's the assumption that we're going to make. And under that assumption, we're going to derive what is the value of our observed rate of recovery for people that do not receive treatment. So by definition, this is equal to the conditional probability of the potential outcome associated to no treatment conditioned on treatment. This is definitely not equal to just the probability of the potential outcome being equal to 1, because, I'm missing like a subscript here, because of the fact that in our data set, treatment and the potential outcomes are not independent because of age. Basically, we saw that treatment is much higher for young people, and those young people have different potential outcomes. So because of age, there is a dependence between the treatment and the potential outcomes. So this is definitely not true. Okay? So we apply just the definition of conditional probability here. And now what we need to do is we need to incorporate age, because we know everything conditioned on age. So law of total probability, we include age in our computations, and now we split this using the chain rule. So we multiply the marginal of age times the conditionals of the potential outcome given age and the treatment given age. And here what we're doing is we're imposing that these guys are conditionally independent given A, okay? Because otherwise by the chain rule, we would also have to condition here on the potential outcome. So what expression do we get for the probability that someone recovers if they're not treated? We get an expression where we can actually cancel out the 0.5s here, okay, because they appear up and down, and we see that this and this adds up to 1. So we just obtain this expression where we have basically the rate at which young people recover if they're not treated, multiplied by how many of those patients do not receive treatment. And then we also have the rate at which the old people recover if they don't get treatment, multiply by how many of them do not get treatment. And the issue here is that there's a strong confounding factor in the sense that this number is completely going to be governed by these two numbers, which is how much treatment we're giving to young people and old people. This is completely distorting the rate of recovery that we observe. This rate of the recovery is very small because of the fact that instead of having 0.5 here, which is the fraction of young people in the population, which is what we really would want to have there, we only have 30% because it just so happens that young people are receiving treatment more often, like 70% of them are receiving treatment. Conversely, this number is very high, which is driving down the recovery rate, right? Because the recovery rate of old people is very low because old people are not getting the medicine. So what I'm getting at is that this number is much smaller than it should be because we're giving the medicine to young people, even though it's useless and it's kind of ironic, right? Because what's driving down here the rate of recovery when you don't get medicine is the fact that you're not giving the medicine to young people for whom this doesn't really work. And you're giving it to the old people who just have poorer health in general. So that is driving down the recovery, not the actual efficacy of the drug. You can see this perhaps even more clearly when we look at the potential outcome of what happens when you do get treatment. We're going to apply exactly the same idea. We want to see the observed recovery when the patient is treated. This is equal to the potential outcome associated to treatment, but conditioned on treatment, okay? Conditioned on treatment, and that's super important. Now, we're going to apply the definition of conditional probability. We're going to plug in age, and we're going to expand this in terms of the old people and the young people, and then the conditional probabilities. We can factor that again because we're assuming conditional independence given age. And we get to the point where, again, we have an expression where what really matters here is how many young patients we're treating and how many old patients we're treating. Because we're treating so many young patients, this drives up the rate of recovery, even though for those patients we know that the drug is completely useless. Okay? Again, ideally we would have here 0.5 and 0.5 because that's the fraction of young people and old people in the population, but this is distorted by the fact that the treatment rates depend on age. And then age also affects the potential outcomes. And that's what a confounding factor is. A confounding factor is some factor associated to the treatment. So basically a factor according to which the treated group and the untreated group is systematically different. And it also needs to produce a difference in the potential outcome. So in this case, young people recover much better, even like independently from the drug, and they are also treated more often. So this boosts the apparent efficacy of the medicine. Okay, so this is, larger than this, just because we're treating more young people and less old people, and the young people in general are healthier regardless of the medicine. So can we correct for this? Can we correct for the confounding factor? What we really would like to do is we want to estimate the probability that the probability of the potential outcome being equal to 1. In this case, the potential outcome associated to no treatment. We can do this by conditioning on age and then multiplying by this conditional probability of the potential outcome given age. So now we have to ask ourselves, do we know the terms in this equation? P of A, this is just the probability that a patient is old or young. We know this, it's 50%. The more interesting question is, do we know the conditional potential outcomes given age? And in fact, we do, but under an assumption. This is the assumption that we made before, where we said that the potential outcomes and the treatment are conditionally independent given A. You can imagine this as if you were doing a randomized trial within each age group. Or in other words, if within each age group, you're guaranteed that the treatment group and the control group or untreated group are not systematically different. There are no other confounding factors. If that is the case, then this conditional independence assumption holds. And as we will see, we are able to adjust for the confounding factor as long as we know it. So what do we actually observe from the data? We do observe the recovery rate for young people that do not receive the medicine. For those people, just by definition, the observed recovery is exactly equal to the potential outcome associated to not being treated, because we are conditioning on no treatment. So we do get to see that, okay? Conditioned on no treatment. But now if the conditional independence assumption holds, because we're conditioning on young here, and the conditional independence assumption essentially captures the fact that there's no systematic difference between the treatment group and the control group among young people, then this is exactly equal to the probability that we want, which is the conditional probability of the potential outcome associated to no treatment conditioned on young. This is as if we were lucky and we have like a randomized trial within the young people. This is what we're assuming. Exactly the same for the potential, and that's 0.8, okay, 80%. Exactly the same for the potential outcome associated, I'm doing it the other way around. Exactly the same for old people. So we're still looking at the potential outcome associated to no treatment, but now for old people, again, if we assume this is just by definition, the observed rate of recovery is equal to that potential outcome associated to no treatment, as long as we condition on the treatment. But if we're also conditioning on the age, under our assumption, we can actually remove that conditioning on treatment. And this is actually going to tell us the recovery rate for old people, which is going to be 0.2 as we had established. And now I can say the same thing for the potential outcome associated to treatment. We assume conditional independence. This is just by definition because we're conditioning on treatment being equal to 1. So we do see that potential outcome conditioned on treatment being equal to 1, but we're also conditioning on age. And by the conditional independence assumption, which again just captures the fact that we have this idealized situation where among the young people we have no consistent difference between the treatment group and the control group, and the same for the old people. Then we actually do get to see the conditional probabilities of the potential outcomes given age. And now what we can do is we can go back and combine them, right? So we wanted this. These are just actually equal to the observed probabilities of recovery as long as we condition on age. This should be an A. Of course, had a typo. This is because the example used to be a little bit different. It wasn't age, it was a gene or something. But anyways, don't worry about it. And then we actually get the right answer. Okay, the potential outcome associated to no treatment is 0.5, which is exactly what we wanted to estimate. So in this fictitious example, because of the fact that we're assuming this conditional independence assumption when we're building the data, this actually holds exactly. In reality, it will be difficult to guarantee that you don't have other confounding factors. Same thing for the potential outcome associated to treatment. We do exactly the same thing. This we know is 0.5, and this we get from the observed values. Here again, I have my typo. And we just plug in the values, and this is A. Okay, so by looking at each subgroup where there is no significant difference between the treatment group and the control group, we're able to get a very accurate, I mean, in this case, perfect because it's an idealized example, but we get an accurate idea of the causal effect. So the medicine actually improves things, but only by 10%, not by as much as we had observed just from the data because of the confounding factor. So the problem in practice is that it is impossible to identify all confounders. What can we do? Well, if you can, you do a randomized control trial, you do a randomized experiment where the potential outcomes and the treatment are independent. I mean, you definitely should do that if you can. If you cannot, you still should adjust for the confounders that you know about, because this will give you a better idea of what is going on, but you cannot guarantee that there might not be other confounders. Okay, so that's all I got. What we have learned is that causal inference from observational studies is very challenging due to the presence of confounders such as age in our running example. We have explained how to adjust for those non-confounders under this conditional independence assumption, which means that there are no additional confounders. And that's it. Thank you very much.